Okay, now I'm going to do a relativistic problem again that includes particle physics and relativity, combination of the two. I have a neutral pion here that is traveling like this, right? The neutral pion is traveling with a certain kinetic energy, and then it decays into two gamma ray particles, like this, two gamma ray particles. And then each gamma ray particle can have the same angle, but it can be different angles. So let's say this angle here is theta. So what's going to happen if the angle theta is 30 degrees versus the angle theta is, let's say, 60 degrees? What is going to be the what's going to be the initial kinetic energy? So if it's 60 degrees, if the gamma is 60 degrees, that means initially the pion wasn't traveling that fast, right? That means the two gamma rays that split off at a higher angle. If the pion travels faster and it decays into two gamma ray particles, then the angle should be smaller. So that's kind of our hypothesis, is that I believe if the pion it has more kinetic energy, the gamma rays that it decays to will have a smaller angle. So let's do the calculations, okay? So what two quantities are conserved here? Momentum and the total energy of the system, right? But the relativistic momentum equation and the relativistic total energy equation, right? So the momentum of the pion must equal to the total momentum of the gamma rays in the x direction, right? So the total momentum, so we're going to say momentum of the gamma cosine of 30. So we'll first solve the case where the angle is 30 degrees. Right. So the momentum of the pion is going to be what? Well, that's equal to the square root of the energy of the pion squared minus the rest energy of the pion squared, right? So remember the equation that I'm going to use for momentum is that it's square root of energy squared minus the rest energy squared over c. So the rest energy of the pion is going to be 135 mega electron volts. 135 squared over c. Okay, the rest energy of the gamma particle is 0, so the momentum of the gamma particle is just equal to its total energy, the total energy of the gamma. So since this is 0, it's just going to be the energy of the gamma divided by c. Okay? But the energy of the gamma is the same thing as the kinetic energy of the gamma, right? Because there is no rest energy. So we can say this is just equal to the kinetic energy of the gamma, right? Times cosine 30. Times cosine 30. Okay? So now what we have to do is actually we have to double this because each one has its own momentum, right? Momentum of the gamma this way times x, momentum of the gamma cosine 30. This one also has momentum of gamma cosine 30. Right? So it's 2 momentum gamma cosine 30, 2 energy of gamma cosine 30, 2 kinetic energy of gamma cosine 30, right? So then we just have here e pi squared minus 135 squared. Okay, so cosine 30 is going to be what? Root 3 over 2. Root 3 over 2, so the 2 cancel. So it's just going to be square root of the energy of the pion squared minus 135 squared is equal to square root of 3 kinetic energy of the gamma. Okay? Now we have to conserve the energy of the system. The total initial energy of the pion, okay, must equal to twice the energy of the gamma, right? But the energy of the gamma is the same thing as the kinetic energy of the gamma. So for energy equation, we don't worry about its direction either. We just say the energy is just energy, it's a scalar. Okay, so then we say twice the energy of the gamma, but the energy of the gamma is the same thing as the kinetic energy of the gamma. Okay, so then we say energy of the pion is equal to twice the kinetic energy of the gamma, but the square root of the energy of the pion squared minus 135 squared is square root of 3 kinetic energy of the gamma. So now we can kind of put these together, right? We can say here, I can put this one in here, I can say energy of the pion is twice the kinetic energy of the gamma, so then square that, okay? So square root of, so e pi, so this is going to be 2 kinetic energy of the gamma squared minus 135 squared is equal to square root of 3 kinetic energy of the gamma. So then I can square both sides, then I'm going to have here 4 kinetic energy of the gamma squared minus 135 squared, and then I'll get rid of the square root, and then if I square that, I'll get 3 kinetic energy of the gamma squared. Okay? So then what's going to happen, take this over to the other side, then I'm just going to have kinetic energy of the gamma, right? Kinetic energy of the gamma squared is going to equal, this one goes to the other side, 135 squared, and then the kinetic energy of the gamma, 135 mega electron volts. Okay, so if this is 30 degrees, each gamma particle is going to have a kinetic energy of 135 mega electron volts, which is the same as the rest energy of the pion, right? Which is 135 mega electron volts, right? Okay, now what's going to be the total energy of the pion? The total energy of the pion is going to be twice the kinetic energy of the gamma. So the total energy of the pion is going to be 270 mega electron volts. Okay? What's going to be the kinetic energy of the pion? Well, then you can say the energy of the pion is equal to the kinetic energy of the pion plus the rest energy of the pion. E0 of the pion. Well, here's the story. The pion is coming with a kinetic energy of 135 mega electron volts. It also has a rest energy of 135 mega electron volts. So its total energy is 270 mega electron volts. It will spontaneously decay into 2 gamma particles, right? And the 2 gamma particles will each have kinetic energy of 135, traveling at 30 degrees. Their y components of momentum will cancel, and their x component of momentum will add up to equal to the original momentum of the incoming pion, right? So this will conserve energy and it will conserve momentum. Of course, it will also conserve charge. You have to be able to conserve charge, baryon number, strangeness number, lepton number, all those other things, right? So now, what would happen if the angle was 60? Okay, what's going to happen? Let's figure that out. So if the angle was 60, this will change to cosine 60. Okay, this equation will still stay the same. So then cosine 60 is going to be what? That's going to be a half. So you're going to be missing the rad 3. It's just going to be, instead of rad 3 over 2, it's going to be 1 over 2. Okay, so then this is going to cancel. And then the 2 and the 2 cancel, and then you're just going to have your kinetic energy of the gamma. However, this equation will still be true. Okay, the energy equation does not depend on the direction of the decay, right? So then you can put this in here again, minus 135, but you're missing the root 3. You just have k gamma, right? So then you square both sides. You get here 4k gamma squared minus 135 squared, and then you square this, you get this. Okay? So now what's the answer going to be? Okay, so then you're going to have 3k gamma squared is going to be 135 squared. K gamma squared is going to be 135 squared over 3. And then k gamma is going to be 135 over root 3. So therefore the kinetic energy of the gamma is less now, right? Because it's going at a higher angle. Okay? So what is that going to be? 77.9 mega electron volts. So you see that it's a lot less than the kinetic energy if it's 30 degrees, right? So then what's going to be the energy of the pion? The energy of the pion, the total energy of the pion is going to be twice the kinetic energy. So multiply this by 2. So that's going to be 155.9 mega electron volts. Okay? Then what's going to be the kinetic energy of the pion? So then here, instead of 270, we put here 155.9. 155.9 minus 135, that gives you the kinetic energy of the pion, right? Kinetic energy of the pion, 155.9 minus 135. That gives you 20.9 mega electron volts. So the story behind this is now this. In this case, the pion was coming much more slowly. Why? Because it has less kinetic energy. 20.9 mega electron volts versus 135 mega electron volts kinetic energy. So that's kinetic energy is about 6 times less. So the velocity is also quite a bit less, right? So it's traveling a lot slower. Then it decays into two gamma particles. The gamma particles travel at 60 degrees this way, and they're both going at the speed of light, of course. Gamma particles will always go at the speed of light, but they have less momentum and less kinetic energy, right? Why? Because they have less total energy, okay? The energy of the gamma particle is going to be based on its frequency, right? So if the energy is equal to, let's see, what is the energy of the gamma particle? In this first case, the energy of the gamma particle is equal to 135 mega electron volts, right? That's the same thing as its kinetic energy. So the energy is the Planck's constant times its frequency, 135 mega electron volts, right? If it's 60 degrees. If it's 30 degrees, right? So now what's going to happen? If it's 60 degrees, energy and the kinetic energy of the gamma particle is dropping from 135 all the way down to 77.9. So what is actually happening to that gamma particle? Its frequency is dropping by the ratio of 135 to 77.9. So it's going to be a little bit less dangerous of a gamma particle. The frequency drops from 135 to 77.9, so that's about a half a drop of frequency. Okay? If its frequency drops enough, it might not even be a gamma particle. It might end up being a X-ray particle, right? In the electromagnetic spectrum, right? You have all kinds of spectrums. The frequency less, the electromagnetic wave that has less frequency and less energy than the gamma ray is the X-ray, right? So if the frequency drops enough, and if this goes kind of at a steep angle, you might actually turn into an X-ray instead of a gamma particle. You see, so the idea what's happening, when the energy is dropping and the kinetic energy is dropping, the frequency is also dropping. Okay, so that why? Because the initial pion that is traveling slower. Instead of having a kinetic energy of 135, it only has a kinetic energy of 20.9 mega electron volts. So it's good to solve some of these relativistic particle physics problems, but also try to understand what is happening. What is the difference of the answers? Why is 135? Why is 120? And then what is that signifying? Why is that happening? Okay, so try to make sense of everything that you solve. Thank you very much.